Are you in?
No, I've got the green light.
Yeah,
Okay, yes. Good. So I want to start with a disclaimer. This is a talk with no new results. I just think it's a story that should be better known. I want to exhort you to think about the problem of cubic fourfolds and their rationality in particular. And mainly the point of this lecture is to sort of give you a summary of what we know and what we don't know, and to convince you that it's an interesting problem. And so it will not have any new results. The good side of that is it should be a short talk, and it should be something I would hope you can follow. If you have any questions along the way, please stop me and ask. So as I said, I'm trying to sell you something. I'm trying to sell you some snake oil. And the basic premise here, the overarching premise, is that cubic hypersurfaces are good things to study. That throughout the development of algebraic geometry, from the very early days, post-Renaissance, somehow the case of cubic polynomials has been pivotal in our understanding of the geometry of varieties. It's, I mean, that makes sense, right? Because linear equations we know how to solve. Quadrics are kind of a gray area. And where we really hit, our limits, typically, is when we first start talking about polynomials of degree bigger than 2, namely cubics. But I want to make that point in sort of sequentially. In the first occurrence, and this is stretching a point a little bit, but no, I mean, it was a big deal when they first figured out how to solve simply a cubic polynomial in one variable, to write out the roots as in terms of the coefficients. That was huge. And it was back in the day when, I don't know if, I'm not a historian of science or mathematics, but this is in the days before universities, as we know, before math departments. And what people would do is, I mean, mathematics was largely, they would challenge one another to what were called disputations. And if you engaged in a disputation with someone else, you would make up a series of problems that you know how to solve and present those problems to the other person, and they would do likewise. And whoever solved more of the other person's problems would be declared the winner of the disputation. And yeah, we could try it. It's got to be better than what we. In fact, there was a fair amount of money was usually at stake, and as well as status, prestige, position, and so on. And these guys cleaned up because they knew how to solve cubic polynomials, and no one else did. And they weren't going to just publish a paper and tell everybody how to do it. They just sort of cleaned up on the disputation circuit. And until, it's kind of a sad story. When I gave this talk once before in front of Robin Hartshorne, who is a historian of mathematics, he pointed out that this is a vastly oversimplified account of the story, that in fact, people didn't just all of a sudden get what we now recognize as the formula for the roots of a cubic polynomial. They sort of did it for successively larger and larger classes of cubics. And Tartaglia, for example, who was the reigning champion of solving cubics for a long time, still didn't have the most general cubic, the solution of the most general cubic. Someone else came along who figured that part out and cleaned his clock. And he died actually penniless and as a result of this. So before you publish your next paper, bear that in mind. What did emerge from all this was the beginnings of the presence of complex numbers. This was in some sense where people first began to see the appearance of complex numbers in mathematics. This is probably my best example. In the 19th century, people encountered cubic plane curves, initially in the context of analysis, when they were trying to evaluate what are now called elliptic integrals. And having figured out how to involve, how to integrate in closed form, functions that involved a square root of a quadratic polynomial. They assumed that they could do it for cubics as well, and they hit a brick wall. And a large part of what drove 19th century mathematics was trying to figure out why. And the central fact that makes elliptic integrals so much harder than ordinary trigonometric integrals is exactly the fact that the cubic curve in question is not rational. And this has an effect in many ways. All the standard trigonometric substitutions that you do when you solve, when you integrate functions involving square roots of quadratic polynomials, they all amount to parametrizing a rational curve in the plane by P1 and just pulling your differential form back and getting the integral of a rational function. But you couldn't do that with a cubic because it's not rational. And what's more, the fact that topologically the complex locus now has non-trivial one cycles, meant that the integral was only well-defined up to a pair of independent periods, which in turn meant that the inverse of that indefinite integral would be a doubly periodic function in the complex plane. And that's a clear indication that it's not an elementary function. It's not something that people knew how to deal with. So this gave rise to an awful lot of 19th century mathematics. In the later half of the 19th century, when people began to look at surfaces as well, one of the first things that was discovered, I'm not even sure who by, was that cubic surfaces are rational. Again, very much in contrast to the case of curves, cubic surfaces are rational, and they're realized as the plane blown up at 6 points, or P1 cross P1 blown up at 5 points. And in general, this was sort of the first really meaty example of birational geometry that people encountered. In the late 20th century, there was the theorem of Clemens and Griffiths. They looked at cubic threefolds. Cubic threefolds had been studied for some time before. People discovered fairly early on that cubic threefolds were unirational. They admit in fact, a degree 2 map, a rational map, degree 2 from P3. But they couldn't find a rational parameterization, and Clemens and Griffiths in 1972 showed that in fact you can't, that they're not rational. And so that was the first example. We have others now, but that was the first example showing that rationality and unirationality do not coincide in higher dimensions. And looking ahead, again, I'm trying to sell you on this. It's the case of cubic fourfolds is still very much open, and it has the potential to give us an answer to a number of questions about the qualitative behavior of the condition of rationality. So that's what I'm going to talk about today. I want to talk about, first of all, what's at stake, what's involved, what we might learn from knowing more about rationality of cubic fourfolds, and why we think that. So first, the first thing to do is to notice that in all the examples, the cubic plane curves, smooth cubic plane curves are never rational. Smooth cubic surfaces are always rational. Smooth cubic threefolds are never rational. The point is that in each case, we have a family of smooth projective varieties, and they're all either rational or all non-rational. And the question we can ask is the same thing true in general? In other words, if I have a family of smooth projective varieties over some base B, and I look at the locus in the base where the fiber is rational, is that an open subset? Is it closed? In other words, is the condition of rationality open or is it closed? In every known example, and by the way, when I say known here, I mean where we know the answer, not just a family of varieties, but one where we know exactly which fibers are rational. In every example where we know that, it is the case that the condition of rationality is both open and closed. And that accounts for what we've observed in the case of cubic curves, surfaces, and threefolds. And again, the question is, are these things true of the condition of rationality in higher dimensions? just to make it clear, we know this for curves and surfaces, because in the case of curves and surfaces, rationality can be detected by means of suitable numerical invariance. There's the, rationality for curves is just genus 0. For surfaces, there's the theorem of Casanova and Enriquez that says the surface is rational if, P2 and Q are both 0. They're numerical invariants that behave well in families, and so you can see that the condition is both open and closed. We do not know this for dimensions 3 or higher. So that's the sort of what I view as probably the most central question that we might hope to answer based on cubic fourfolds. And the answer to both questions, there's two independent questions here. Is the condition open? Is the condition closed? And what I hope to show you today is that the expectation is that the answer is in fact no for both questions. In fact, specifically, what I'm going to try to explain to you is the sort of logic behind our expectation that if we look at the space of smooth cubic fourfolds, in fact, they're not all rational and they're not all irrational. Instead, the ones that are rational seem likely to form a countable union of subvarieties in the space of all cubic fourfolds. It's neither open nor closed. In fact, it's more of an arithmetic condition than a geometric one in some sense. Sort of condition that can hold on a countable dense subset of a space, but not on any open or close, any open subset is typically think of as an arithmetic condition. So that's what the talk is going to be about. So let's start with just saying what we know about cubic fourfolds, okay? And since we're talking, the whole point is to talk about the family of cubic fourfolds, the first thing we should ask is what the moduli space. Is there a moduli space? Of course, there is a moduli space. You can just take, I'm not the person to ask. Radu would be the person to ask about this. But you can just take the GIT quotient of the open subset of the projective space of smooth cubic fourfolds. That has dimension, the dimension of the space of cubic fourfolds, that's H choose 3 minus 1, minus the dimension of PGL 6, and that comes out to 20. So it's a 20-dimensional family of cubic fourfolds. The Hodge structure, or the cohomology of the cubic fourfold, by Lefschetz, there's no interesting cohomology, so to speak, except in the very middle dimension, in H4. And the Hodge decomposition it's 20, the H4 is ranked 23, and the Hodge decomposition has dimensions 0, 1, 21, 1, and 0. So that's the picture of the cohomology, or specifically the Hodge decomposition. Now notice in this situation where we specify where the dimensions of the Hodge groups, H31, H22, and H13, the dimensions of the first and last, the dimension of the first one in particular, H31, is just one-dimensional. Now, if you specify that one-dimensional subspace of the cohomology, then, of course, that determines the H13, the opposite one, because that's just the complex conjugate of H31. And the middle cohomology group, the middle piece of the Hodge decomposition, H22, is just the orthogonal complement of the direct sum of those two. So the Hodge structure is specified completely just by specifying that one-dimensional subspace H31. Now, H31 can't be completely arbitrary. For one thing, it has to be orthogonal to the square of the hyperplane class. We always have a class in H4, which is the square of the hyperplane class. That lives in H22. So it must be orthogonal to H31. So going in the other direction, H31 has to be orthogonal to that one-dimensional subspace spanned by omega squared. In addition, it must have self-intersection 0, because if I take the wedge product of two 3-1 forms, I get 0. And finally, this is the more subtle part, and I don't even remember the right inequality. It's the the value, the cup product of a 3-1 class with its conjugate has a sign. It's either positive or negative. It's one of the two. Okay, so what does that mean? It means, okay, so first of all, when we restrict to the orthogonal complement, specifying H31, it's just a one-dimensional subspace of a 23-dimensional space, so that corresponds to a point in P22, right? Well, I restrict to the hyperplane, which is orthogonal to omega squared, that gets me down to a P21. Now, I need, the first of those conditions says that its cup product with itself is 0. That's a quadratic condition. So that restricts us to a quadric hypersurface in P21. And the last condition simply says that we're in a complex analytic open subset of that quadric. So altogether, the set of possible Hodge structures is 20-dimensional. It's an open subset, complex analytic open subset of a quadric hypersurface in a P21. So it's 20-dimensional. And of course, that was exactly the dimension of the moduli space. And now we have a theorem, it's a really key theorem of Voisin's, which says that in fact, the strongest possible Torelli theorem holds. That the Hodge structure of a cubic fourfold determines the cubic fourfold. And what's more, at least an open subset, open dense subset of all possible Hodge structures do occur. Now, that, I want to just focus on that last statement. If I look at all possible Hodge structures, at least an open subset of them do occur. Now, what that means, among other things, is that on a very general cubic fourfold, the Hodge structure is irreducible. It's not a direct sum of smaller Hodge structures. Because, again, among all possible Hodge structures, those that are direct sums, those that are even direct sums over Q, form a proper subvariety, or a countable union of proper subvarieties. If Voisin is telling us that a general Hodge structure occurs as the Hodge structure of a cubic fourfold, that says that for a very general cubic fourfold, the Hodge structure is irreducible. Even over Q, it's not a direct sum of smaller Hodge structures. And what that means in particular is, I mean, the sort of first immediate consequence of that is that there's no other algebraic cohomology beyond the hyperplane class squared, beyond the one algebraic cohomology class you know must be there. You see, I mean, if we had another algebraic cohomology class, another element of H22 over Z, we would have another summand, at least over Q, we would have a summand of the Hodge structure. And the picture here, which is left over from the pre-talk, is the crucial one. I've even changed the numbers to make it reflect the fact that we're dealing with fourfolds rather than surfaces. Basically, we have this four-dimensional cohomology of X. Sorry, this should be an H4. I didn't quite fix it all the way. And what we're saying is that the algebraic cohomology, the portion of the cohomology that's represented by fundamental classes of algebraic surfaces, is contained in the intersection of the integral lattice with this subspace H22. And this is the picture. Imagine that this lattice here is the integral fourth cohomology, and the subspace H22 is here. And Voisin is telling us that this subspace is moving freely, except, of course, for the condition that it has to include the omega squared. And if you believe that, well, who would not believe Voisin? Then what that says is that for a general such cubic fourfold, and correspondingly a general such Hodge structure, there are no other lattice points in that subspace H22. So every surface on such a cubic fourfold is homologous to a multiple of omega squared. It's homologous to a complete intersection if it's not a complete intersection itself. Another thing we know is that the Hodge conjecture is true for cubic hypersurfaces. We haven't used this, and we're not going to. For example, here I wrote equality, which is the expression of the Hodge conjecture in this case. All I really used, though, when I was discussing this a moment ago, is the inclusion. So we're only going to use the sort of elementary fact that the algebraic cycles are contained in the intersection of the integral cohomology with the H22 subspace. But it's good to know. It's good to know that we have the full strength of the Hodge conjecture for cubic fourfolds. All right, so that's the base background on cubic fourfolds. Now I want to tell you what we know about rationality of cubic fourfolds. And this is going to be a very short slide. There it is. Some smooth cubic fourfolds are rational. So let me just give you an example of that, okay? I want to imagine we have a cubic fourfold, and it contains two skew two-planes, L and M. And you have to check for yourself that it's not hard, that there are, in fact, we'll write down equations for something like that in a moment. There are such smooth cubic fourfolds. In fact, they form an 18-dimensional subvariety of the space of all cubic fourfolds. If we have these two skew two-planes, L and M, we get a birational map from the product L cross M to X by sending a pair of points on L and on M. Given a point on L and a point on M, we draw the line joining them, and that line will typically meet the cubic fourfold in one additional point. So we send that pair of points on L and on M to the third point of intersection. And this is a birational map because every point, at least other than those lying on L or M, every point in P5 lies on a unique line that meets both L and M. So we have an inverse map, rationally at least. In fact, specifically, what we can say is, if you think about it, going the other direction, from X to P1 cross P1, the reciprocal of this, let me back up just a second. So the reciprocal of this map, not reciprocal, the inverse, basically what it does is it blows up L and M, because this map is not defined in the other direction. The map backwards is not defined at points of L or M, so we blow those up, and then we simply collapse all the lines lying on the cubic fourfold that met both L and M, or equivalently all the lines joining L to M that lie on the cubic fourfold. They get collapsed. So the map is a particularly simple map. It just blows up L and M and collapses this family of lines. And the same idea can be applied somewhat more generally if we have, for example, a surface in P5, which is a quartic scroll. That's one of the basic examples of a rational normal surface scroll. And it's a surface of minimal degree 4 in P5. And it's just gotten by taking two conics in complementary planes and choosing an isomorphism and joining corresponding points. You could just construct it directly by starting with P1 cross P1 and embedding it in P5 by the space of bihomogeneous polynomials of bi degree 1, 2. The point is that surface has the property that its secant lines fill up P5 once, meaning a general point in P5 lies on a unique secant line to that scroll. There are not many surfaces with this property. You probably know that the Veronese is the unique surface whose secant lines don't fill up P5. Well, you can also try to classify surfaces whose secant lines fill up P5, but only once, like this. And in fact, this is pretty much it. That means that if we have a cubic fourfold that contains such a surface, we get a birational map between pairs of points on the surface to X. Again, given a pair of points on the surface, we draw the line joining them and look at the third point of intersection of that line with the cubic fourfold. And again, the fact that a general point in P5 lies in a unique such secant means that this is a birational map. Finally, we just have to check that the symmetric square of P1 cross P1 is in fact rational, and then we know that X is. This actually gives us a 19-dimensional family of rational cubic fourfolds, which in fact, it's not obvious, but it does include the family of cubic fourfolds containing two planes. Okay. What is all this, what does the Hodge theory and so on have to do with rationality? Well, this is an idea that was introduced, I guess, by Clemens and Griffiths in their paper on cubic threefolds, that when we know that any birational map can be factored into blow-ups and blow-downs. Okay? And we could ask, what happens to the Hodge structure of a variety when we blow up, or correspondingly when we blow down? And the answer is straightforward. When we blow up a point or a curve, we add only, so to speak, trivial summands to the Hodge structure. We blow up a point, for example, right? We introduce a new algebraic cohomology class, namely the class of a P2 living in the exceptional divisor. And the new cohomology, the cohomology of the blowup, is in dimension 4, in degree 4, is just the direct sum of the old with this one extra class. And the one extra class lives in H22. So basically, the new Hodge structure is just the direct sum of the original Hodge structure with this trivial one-dimensional Hodge structure. And the same thing is true if we blow up a curve. We're just going to get we're not going to get anything interesting in the Hodge structure. It's only when we blow up a surface that we see something interesting happening to the Hodge structure of the fourfold. What happens is that we get, again, the Hodge structure of the cohomology of the blow-up added, is just the direct sum of the cohomology of the original fourfold with the middle dimensional cohomology or primitive cohomology of the surface. And the same is true in the level of Hodge structures. The Hodge structure of the blow-up is just the direct sum of the primitive Hodge structure of the surface you blew up with the Hodge structure you started with. So what does that mean? It means that if there was a birational isomorphism between a cubic fourfold and P4, you would get it by a sequence of blow-ups and blow-downs. Each step you would introduce as a new direct summand a new piece of Hodge structure, or you'd get rid of one, right? But now, because the primitive Hodge structure of a very general cubic fourfold is irreducible, right? We said as a consequence of Voisin's theorem, it can't come to you in bits and pieces. It has to just show up all at once. In other words, we follow the sequence of blow-ups and blow-downs, right? Starting with P4, winding up with our cubic fourfold. At some point, we have to see the entire Hodge structure, primitive Hodge structure of the cubic fourfold appear in one piece, which means that that Hodge structure has to appear as a direct summand of the primitive Hodge structure of a surface. We would have to blow up, in other words, a surface that carries that Hodge structure, at least as a direct summand of its Hodge structure. And we don't know any such surfaces. That's not to say that such surfaces don't exist. Otherwise, I'd be telling you a theorem and not just speculating. But in fact, I don't think it's reasonable to expect that such surfaces do exist. Basically, yeah.
I believe Alcon proves such surfaces do exist. Don't you have a paper about this?
Well, that's what I was just asking about that, but I don't.
No. It's not a summand. It's just a quotient.
Oh, it's just a quotient.
Yeah.
Sorry for the interruption.
No. But I'm glad you mentioned that, because I was trying to find that paper and I couldn't. It's not on MathSciNet, at least as far as I could find. Well, that's what I know you told me, but I looked for it and I couldn't find it. All right, never mind. We'll straighten this all out. Okay, so let's scratch that we and put in a first person pronoun. I don't know of any such surfaces. But again, the expectation is, I think, that they don't exist. And the upshot is that if that was the case, then in fact a very general cubic fourfold is not rational. So already, if that's the case, we see that the condition of rationality cannot be both open and closed in higher dimensions, in families of smooth projective varieties.
What is the property of surfaces of which you know no such surfaces?
That it's, let me back up just a second. No, there we go. So it's a smooth surface that contains this primitive Hodge structure of the cubic fourfold.
No, I mean,
As a,
it has the right dimensions, or has like which property of the Hodge structure, the primitive Hodge structure of cubic fourfold? Which property of the Hodge structure of the cubic fourfold are you looking for in the surface?
I want that Hodge structure, not a property. I want that Hodge structure to appear itself.
As a direct summand.
As a direct summand of the Hodge structure of the surface.
And can you like write down some characterization of the Hodge structures of cubic fourfolds and just then go?
No, well, the whole point is Voisin's theorem tells me that the Hodge structure of a general cubic fourfold is just a very general Hodge structure. You just take a random one-dimensional subspace, H31, and that's it. That's a Hodge structure of a cubic fourfold. Again, because it's irreducible, if it appears in the course of blowing up and blowing down, it has to appear all at once by blowing up a surface that contains that Hodge structure. And again, it contains that Hodge structure as a direct summand, and again, we don't know of any. So that's the situation. And that's a reason for believing that its general cubic fourfold is not rational. But again, yeah. So, yeah. Okay. Yeah.
Why do you think that it's unlikely that such a just because we don't know an example?
No, it's more than that. I mean, it's the Torelli theorem of Voisin's, that this is a very general Hodge structure. That's very rare. You see, in general, Torelli theorems, you don't expect them to hold. At least not surjectivity. Injectivity, yes. There's all sorts of theorems in various contexts that say that Torelli map is injective in one sense or another. But surjectivity is much harder if you just look, like for example, at quintic surfaces. If you go to quartic surfaces, they're K3s, you have the surjectivity of the Torelli map. But in any higher degree, the space of surfaces in P3, say quintics, right, is tiny compared to the space of all Hodge structures. And that's the general phenomena that we see. Outside of a few very low rank or low degree cases, you don't expect to see a general Hodge structure appear as the Hodge structure of a variety. And by Voisin's theorem, this is a general Hodge structure. It's not logic, it's just intuition. But it raises, the stakes in some sense. So, all right, so what are we not talking about so far? What we're not talking about is something I'm sure has occurred to most of you. The numbers that we've been dealing with are very similar to numbers that appear in the discussion of K3 surfaces. If I have an algebraic K3, so that means with a polarization, they vary in a 19-dimensional family. The middle Hodge structure is exactly the same, but dimension one less in the middle. And again, it's a theorem that the Torelli map from the space of K3 surfaces to the space of possible Hodge structures is an open immersion. So there's a very similar sort of picture here. And you might hope to relate the Hodge structure of a cubic fourfold to the Hodge structure of a K3 surface. The problem is you are one off. And because the Hodge structure of a cubic fourfold is irreducible, I should say the primitive Hodge structure is irreducible, it can't be, in general, can't have anything to do with K3s. It just have nothing to do with one another. But then we could ask, again, because Voisin assures us that all Hodge structures occur with this lattice, we could ask, well, are there in particular cubic fourfolds whose primitive Hodge structure does contain well, in this case, a rank 1 algebraic summand coming from H22, and then where the rest of it, the orthogonal complement, is the Hodge structure of a K3. And so what we're looking for is exactly cubic fourfolds whose Hodge structure contains a rank 2 lattice of algebraic cohomology classes. Again, that's just the same thing as saying, given that we do know the Hodge conjecture in this case, that the X does contain surfaces not homologous to a multiple of omega squared. Let me just point out that since we're just requiring that this orthogonal complement of H31 contain a non-trivial lattice point, the locus of such cubic fourfolds should be codimension 1 in the space of all cubic fourfolds. It should be a union of hypersurfaces. In fact, if we specify the particular lattice, if we look for cubic fourfolds whose Hodge structure contains a given lattice, gamma, then that should form a hypersurface in the space of all cubic fourfolds. We don't know it's non-empty, I should say. We don't know it's irreducible. But it's codimension 1. So the question is, in that case, if we have such a cubic fourfold, is it possible, so we're assuming now that the middle dimensional cohomology has a rank 2 lattice of algebraic cohomology classes. Is it possible that the orthogonal complement of that rank 2 lattice is, in fact, the primitive Hodge structure of a K3? And finally, if that is the case, is it possible that is this cubic fourfold in fact rational via a map that at some point blows up the K3 surface? This is exactly, in fact, what happened. The example I gave you before, where you have a cubic fourfold containing two planes, L and M, and we get this birational map between the product L cross M and the cubic fourfold. Remember what that map did, going back from X to the product L cross M. It blew up the two planes L and M, and then it collapsed the lines on the cubic fourfold joining L to M, or equivalently the lines joining L to M that lay on the cubic fourfold. You see, and if you want to see what's going on, okay, now I want to write it down in coordinates. I want to choose coordinates on P5 so that the two planes are given by the vanishing of the first 3 coordinates and the second 3 coordinates. And then I want to write my cubic polynomial, the one that defines the cubic fourfold. I want to write that cubic polynomial in those 6 variables as a sum of bihomogeneous terms. It's going to be 4 terms, a bihomogeneous of bi degree 3, 0, 2, 1, 1, 2, and 0, 3. But the condition that L and M lie on the cubic fourfold says that the first and last of those are 0. In other words, we can write the defining equation of the cubic fourfold as a sum of 2 bihomogeneous polynomials in Z and W of bi degrees 2, 1, and 1, 2. And having written it in that way, the locus that we're collapsing when we go back from X to P2 cross P2 is exactly the locus of lines on X, or the lines meeting L and M that lie on X, or equivalently pairs of points in L cross M, such that the line they span lies in X, and that is just the common 0 locus of those 2 hypersurfaces in P2 cross P2. And as you know by adjunction and Lefschetz, if you take a complete intersection of 2 hypersurfaces in P2 cross P2 of bi degrees 2, 1, and 1, 2, that intersection is a K3 surface. So in fact, that's exactly what's going on here. That we start with P2 cross P2, and we blow up a cubic surface, given as this intersection, and then we collapse to threefolds to P2s. And in fact, all examples that we know of cubic fourfolds that are rational fit this pattern. They all have the property that, first of all, they have at least a rank 2 subgroup of algebraic cohomology classes. Secondly, the orthogonal complement of that rank 2 lattice is the primitive Hodge structure of a polarized K3 surface. And finally, the birational map that we have exactly blows up a copy of that K3 surface. So there are by now a number of examples of cubic fourfolds that are known to be rational, and they all conform to this picture. So that's what we want to I mean, and here I'm on shaky ground, but you could even make the case that this is true for a cubic fourfold with a double point. Of course, if a cubic fourfold has a double point, it's automatically rational via the projection from that double point. And the projection from that double point to P4 collapses the lines on the cubic fourfold through the double point. Well, again, if you just expand the equation of the cubic fourfold around that double point, you see you only have a quadratic term and a cubic term, no constant or linear term, because it's a singular point. And the locus of lines on the cubic fourfold that are contained through that double point is just the intersection of the quadric and the cubic hypersurfaces in P4, which is again a K3 surface. So at this point, I want to tell you about what Brendan Hassett did in this, with this idea. And so he basically went ahead and he answered the first two of these questions completely. And he got even started on the third. So again, just to repeat what the questions were, we ask, is it ever the case? Well, of course, we know it is sometimes. But more generally, when does it happen that you have a cubic fourfold with an extra algebraic cohomology class, a rank 2 lattice of algebraic cohomology classes, such that the orthogonal complement is the primitive Hodge structure of a K3? In that case, is the cubic fourfold rational, and is it, presumably rational via a birational isomorphism that blows up exactly that K3 surface? So to what extent does this pattern that we've seen in the examples hold? So Hassett proved three things. The first is he describes exactly the locus of cubic fourfolds where you do pick up the second algebraic cohomology class. It's very nice. Remember I said if you fix a lattice gamma, then the set of cubic fourfolds that contain a copy of that lattice in their algebraic cohomology will form a hypersurface in the space of all cubic fourfolds. Again, I said that's not necessarily non-empty, it's not necessarily irreducible. Hassett answers both those questions completely. He says, you get an if you look at the lattice with discriminant D, you get a hypersurface, an irreducible hypersurface in the space of all cubic fourfolds, exactly when D is congruent to 0 or 2 mod 6 and is strictly bigger than 6. So the picture is that we have the space of cubic fourfolds, and we have now a collection of hypersurfaces indexed by the possible values of the discriminant D, and they give us all cubic fourfolds that have at least a rank 2 algebraic cohomology group. The next question is when, having found this rank 2 lattice in the cohomology, when is the orthogonal complement the Hodge structure of a K3? And he answers that also very explicitly. He says that's the case when D is not divisible by 4 or 9 or any odd prime congruent to 2 mod 3. So, this, I should say, it sounds mysterious, but it's all basically just the combinatorics of lattices. And, given Voisin's theorem that basically you have this one-to-one correspondence between an open subset of possible Hodge structures and cubic fourfolds, it all comes down to just understanding the lattices in question. And this is what comes out of Nikulin's work, basically. Okay. So he has a list, and again, there's an infinite number of these. There's an infinite number of these hypersurfaces in the space of cubic fourfolds that are potential candidates for rationality. Yeah. Oh, I thought somebody asked. The first case, by the way, of this case with the orthogonal complement is the primitive cohomology of a K3 is the case D equals 14. And that's exactly the case that we looked at. So finally, I realized as I wrote this that I'm sort of dating myself. I think I'm the oldest person in this room. Maybe close, if not exactly. It occurred to me that most of you don't know what the $64,000 question is. This was a big game show of the 1950s in which contestants would be asked a series of ever more challenging questions, and if they got them all right, including the last one, they would win $64,000. And so that became part of the sort of common idiom to talk about the $64,000 question. Now it seems kind of dated, I suppose. If we do have a cubic fourfold that is, as I say, a potential candidate for rationality, is it in fact rational? Well, we don't know the answer to that. But we could at least ask for the presence of a concomitant sign. The idea being that, okay, if you get this, if you have a series of blow-ups and blow-downs, you start with P4, you start blowing up, blowing down, blowing up, blowing down. At some point, you blow up a K3 surface whose primitive cohomology now lives inside the Hodge structure of the fourfold and stays there until the very end. Well, when you blew up that K3 surface, you introduced into the fourfold a family of rational curves parametrized by that K3 surface. And that's still there at the very end. So you could ask, in these cases where you have this connection with a K3 surface, can you find on the cubic fourfold a family of rational curves parametrized by that K3 surface? And Brendan finds that the answer to that, again, is yes, at least in, again, an infinite sequence of cases. So again, the logic is, if there were a rational map that blew up a K3 surface, we would see a rational curves parametrized by that surface. And Hassett's theorem is, again, that he gives an explicit sequence of values of D, which I'm not going to reproduce here, but it's an infinite sequence of Ds for which, in fact, the cubic fourfold in question contains exactly what you'd expect to be there, a family of rational curves, in this case lines, parametrized by that K3 surface. So that's seems like at least potential corroboration of the idea behind all this. So that's where we stand, and as I said, now you know as much. In fact, I'm sure many of you know more about cubic fourfolds than I do. You can, despite my trying to be a salesman here, you can decide for yourself whether we have really any reason to believe that that this whole hypothesis is correct. You can see at least why I feel that this is likely. That now, it's true, we don't know much. What we do actually know about rationality of cubic fourfolds was on that very small slide a while back. We know, again, some cubic fourfolds are rational. We don't know that there are any irrational cubic fourfolds. As far as we know, every cubic fourfold could be rational. For all we know, the locus of rational cubic fourfolds could just be everything, or it could be a Zariski closed subset. But in some sense, what all this analysis is suggesting is that the locus of rational cubic fourfolds may well be a countable union of proper subvarieties, namely, in particular, neither open nor closed. And of course, the problem is that we don't really have, at least for now, a way of approaching the problem. It would be nice to know more examples of rational cubic fourfolds, just to see if there's some, if this pattern that the birational parameterizations of a cubic fourfold blow up K3 surfaces. It would be nice to see if that's the case in some more examples. Or, for that matter, we could look at Brendan Hassett's list of potential candidates, potentially rational cubic fourfolds, and see if we can actually find birational parameterizations for some more of the items, more of the cubic fourfolds on that list. The problem is in the other direction. I mean, none of this is really conclusive unless you can show that there are non-rational cubic fourfolds, and for that, we really don't have effective techniques. So at least you might hope to try to approach it by Hodge theory. I don't offhand see a way of doing that. It's not, as I say, I hope I've convinced you it's a problem worth thinking about. It's not a problem, for example, that I would suggest to a student, right? because it's so speculative. If we had a technique that we had any kind of reason to believe would work, then, yeah, by all means go for it. But what I'm suggesting rather is just that you keep this problem in mind. And someday you may find, somebody may tell you something that makes a connection, and you may say, well, I might be able to use that to answer this question. So just keep it in the back of your mind. And that's what I hope you will do anyway. So thank you for your time. And yeah.
Can the middle Hodge structure of a cubic fourfold contain a lattice of rank more than 2?
Oh yes, again by Voisin's theorem. You see, because, now, okay, it doesn't follow logically from Voisin's theorem, because Voisin says simply, no, I guess it does follow. Because, because again, think of this picture here. It's a very crude picture. But imagine, that for this H22, really put in the orthogonal complement of H13, which is a hyperplane. And the hyperplane is moving freely in the primitive cohomology. And Voisin says it's covering an open subset. You see, now, what that means is I can take any sublattice of any rank up to 20, and there'll be a hypersurface, a hyperplane that contains it, and that will be achieved. That will be the Hodge structure of some cubic fourfold. Now, again, Voisin gives you an out. She says you only get an open, dense subset. But still, the set of hyperplanes that contain a sublattice of a given rank is dense. So you have to see some of them. So yeah, so you can look for cubic fourfolds with higher rank algebraic cohomology. Yeah.
What is that? What are we blowing up in this case? So what is this surface that? So say I have a rank 3 lattice. So I look at its orthogonal complement.
That I don't know. I mean, well, you see, that presumably, again, if you believe this whole scheme, the idea would be that the Hodge structure of the cubic fourfold might, in that case, correspond to the Hodge structure of a primitive Hodge structure of a polarized K3 that itself has algebraic curve classes. See, the picture for K3s is very much the same, that a very general K3, the primitive cohomology, has no algebraic classes, but you do see special K3s that have algebraic cohomology groups of any rank up to 20, or 22 if you're in characteristic P. So
is there a nice description of a set of rational curves in P4?
A nice description of
Is it possible to describe it somehow?
the space of rational curves in P4. I mean, there's the conservate space, which is a pretty nice. But is that what you had in mind, or?
I mean, like in P2 we have.
Sorry, I'm not. I think I'm missing the point. No, okay. So look, I don't know. As a way to approach the problem, I don't know. If we're looking for a cubic fourfold that contains, for example, a family of rational curves parameterized by a K3, I don't see any way of approaching that in general. I mean, Hassett does it by looking at lines, and the lines on a cubic fourfold are something that was famously studied because the Fano fourfold of lines on a cubic fourfold is itself a very interesting object. But beyond lines, I don't know that anybody's done anything.
Is it conceivable that the
Irrational locus is not analytically open, it is not some sort of open analytic?
The irrational locus. Yeah, no, that's exactly what we're. What,
I mean, not just in this case. I think in general, it's.
oh, I see. Well, I don't know, but I mean, certainly if in this case, it's neither the rational locus is neither open nor closed. There's no reason to suspect that it would.
But the irrational locus, I mean, at least it's analytically open in this case.
No, it's not. Because again, you see, think of this.
Sorry, yes.
Yeah. I mean, the irrational locus is going to be the complement of a countable dense union of hypersurfaces, according to this belief system. I don't see why everybody else gets to make up their own reality and we don't. Yeah.
For the potentialist rational cubic fourfolds involving a K3 surface, do we know that the child group of one-dimensional cycles of degree 0 on the cubic fourfold is the same as the child group of zero-dimensional cycles in K3?
That I don't know. The child group of zero-dimensional cycles on a cubic fourfold is a complete mystery to me. Pardon?
Well, zero-dimensional cycles isn't it rationally connected?
Pardon me? Oh, I'm sorry. It's rationally connected, of course. I apologize.
One cycle.
You asked about one cycles. I thought you said zero-dimensional. No, again, I don't know. I really don't know. Any other questions?
Okay, if there are no more questions, then the scientific again.